Great. Just make sure the audio sounds good on my phone, as always. It's delay, man. Great. There we go. All right, seemed good enough. See if anyone complains, then we'll know for sure, but good enough for now. All right, let's see what the chat's saying. Suffering yawn drawl. Can we talk about tea? Well, tea's pretty good, but yawn is definitely the bigger tea expert than me. I just drink very basic tea. And then, yeah, Monster Energy. See, I'm not a fan of energy drinks. I like my coffee and my tea, but energy drinks get too crazy. Unless it's like deep into DEF CON CTF or something. Okay, anyways. So I see someone asking about level 7, someone asking about level 5 plus. Okay. So it just so happens that I did have level 7 launch, but we'll start with an earlier level and we'll make sure that we touch on level 7 and such as well. Okay, so, and just to be clear, just in case anyone else is in chat, is there any immediate questions on anything earlier than 5? Because I mean, want to discuss all of the levels to some extent, but definitely makes sense, I guess, to go earlier to later if, yeah, see, if someone's on level 7, so no, they clearly don't care about earlier levels. But I guess since someone mentioned 5, let's take a quick look there. I've heard a few people weren't able to get started. Yeah, I've got this suspicion that whenever we do a 2-week module that half the class or more is going to do nothing for the first week, but it's all right. It's just how it is. Someone else has been ignoring other things to do this module because they know it's the legendary one. Well, yeah, if you complete this as well as all of the previous challenges, you get your yellow belt, so it is pretty legendary. And they, of course, we've gone from embryo to baby to toddler. So, toddler is a whole step above a baby challenge, which I'm sure you're realizing if you're on level 7 that this stuff starts to get a little tricky. Okay, anyways, let's look at toddler level 5. Okay, so immediate impression, it's dumping out the stack to me, so probably some sort of memory corruption going on. It's going to report the stack to me. Stack points to blah blah blah, base pointer, don't care. Does it tell me anything cool? It'd be useful probably if I had the, when I go into these challenges, I actually have no clue which challenge this is by the number. The number means nothing to me. So I don't completely remember the context of what levels came before. So that's why I have to read this. Input buffer begins here, partway through the stack frame. Whatever, okay. Disabled the following standard memory corruption mitigations for this challenge. The stack is executable. This means if the stack contains shellcode and you overwrite the return address with the address of that shellcode, it will execute. Okay, is that it? No, I think there's probably something it's going to tell us at the very end as well on this one. Okay, it's this level. Yeah, this is a cool level. Yeah, so we didn't have levels 4 and 3 last year, so those are new as a lead up to this level. I think this is one of my favorite challenges. So yeah, we have ASLR back. Of course, in the teaching variant, we get to not care about ASLR, but it's definitely useful to solve these with testing in mind. And it doesn't seem like we know all of these things. I mean, we could look for sure to verify in the testing mode, but it looks like all of this is just helpful information. There's nothing like saying, hey, I'm leaking this address to you, for instance, that would imply that that would also exist on the testing level. This all just looks like help information. So ASLR is truly here in this case. Okay, and the interesting thing is that this is going to initialize a seccomp filtered jail before exiting the challenge function. And maybe we want to avoid this. Oh, is level 6? I think level 6 is actually the super cool one that I'm thinking of, but level 5 is also cool. So I guess levels 4 and 5 are new this year and a lead up to level 6, just based off of this avoid it language. Okay. So it allows syscall write and exit group, which probably makes sense. So it only needs 2 syscalls to finish out the program. It just wants to be able to say goodbye and exit. So if it allows these 2 syscalls, the program can just exit normally. So that's probably why it allows these syscalls. Kind of think of this as maybe some crazy last-ditch effort that I don't know how to prevent buffer overflows. So we're just going to seccomp your functionality away, and now you're not actually going to be able to do anything cool even if you achieve arbitrary code execution. It's not exactly the best mitigation. Probably should stop the buffer overflow if this was a real program, but that's all right. Okay, so we allow these syscalls and then it says goodbye. Okay, so so it's telling us to reverse engineer the binary right after this puts call to see the hidden backdoor. So there's some sort of backdoor. We should probably look into what it's talking about. So I'm just going to start with objdump because, I don't know, my favorite reversing tool in the world is objdump. And if it looks like a complete mess, maybe we'll care about something a little more advanced. But let's see if we can understand what's going on with just objdump. There's probably going to be a challenge function. Yep. Okay, so blah, blah, blah. All sorts of stuff. I'm imagining this is going to be near the end. We're looking for this sort of thing, a seccomp resolve, basically some sort of seccomp function. So it's probably before that. Seccomp init. Okay, this could be the puts it was talking about, or I mean, I guess there's several puts. We don't know for sure. Could be this one. Okay, so this jumps out to me immediately, especially if you've done the previous level, and it's talking about this backdoor thing. This number looks insane. It doesn't look like ASCII because we can see that all of these values have, or not all of them, but several of them have the most significant bit of its byte set, which would imply not ASCII. So this doesn't look like some sort of ASCII string. It doesn't look like an address. It just looks like a random value just coming from nowhere. So this could be what the backdoor it's talking about is. So we can see that it's pulling this value off the stack, so some local variable. And maybe there's a relationship between this local variable and the start of our input buffer. And then it's taking this value, so we have RAX, which could potentially be influenced by our input, theoretically, we don't know for sure. Some random massive constant, and then a compare between the two. So that sounds very backdoory to me. So let's just go ahead and see if we can just very quickly bypass this. Let's just use this value. So if we do IPython and we import, I don't know what that was, but whatever. If we import pwn, Control N is not the key we want to be hitting. Pwn context arch equals AMD64. You know what? Why am I doing this in IPython? If I was actually SSH'd in, I would use IPython because then I could use all my keyboard shortcuts and life would be great. I haven't quite mastered keyboard shortcuts while in the browser, so let's just edit an actual script. Because I don't know, we'll just create a new one. x3.py. Okay. What is head of x2? What is happening here? Head x.py. That is getting a little laggy. There's nothing. You know what, I'm just going to open x.py, I don't care. This is, if you're interested, you can pause the video, look at what this crazy nonsense does. I don't really mind. But for now, we are not focusing on that. Okay, we don't care about a GDB script right now. We are not using GDB. We are using process. Don't care about GDB scripts. Okay. This looks cool. Yeah, if you care about what that old script was, you can look back in the video and try and guess what that's doing, and maybe you can ask on Discord. Python x.py. So this script is working. Okay, and then do we still have that value? We do, sweet. So I'm going to not even do any math. We're going to make this real easy for ourselves. We're just going to do target dot right after. So it asks for payload size. So payload size, we are just going to send it 1,000. We're not going to think about this. We could reverse engineer it, actually understand some sizes and stuff if we wanted to, but we are just going to go super quick for this. And I believe it's going to ask us like send payload size or something, or let's see, 100, send your payload. Send your payload. So after it asks us for this, we are just going to be super not caring about this, and we're just going to spam send this value. And maybe if we send this value like 32 times, maybe it's going to hit that RBP minus whatever. That is not a value I can hit. So we want this to end up at RBP minus hex 30. And if we look, I mean, if we really want to be quick about it, we can look at read. See, it calls read somewhere here. We could compute the difference between one of these two values. RAX goes into RSI, which is our buffer. So this, the distance between this and that RBP minus hex 30 is probably what we actually care about. But we're going to make it real simple for ourselves, and we're just going to send it a bunch of times and hope that the alignment works out for us. And then we'll do interactive, and we'll see what happens. See if we can pass that compare condition. Okay, so things happen for sure. It told us you said this craziness. Why? Why is it printing like this? Does interactive actually like not print like unprintable characters and actually do a hex unencode or like an encoding of it? That's cool if it does. All right, we're not going to pay too much attention to that. Has a hidden backdoor, seccomp, jail avoided, continuing execution. So hopefully that shows a bit about what this backdoor thing is. So if you think back to like baby mem level 1, so the very first level of baby mem where you just had to change a value on the stack that was like this win flag thing. So it's a little bit like that. It's a little more, I guess, instead of doing a win for you, it just makes it so seccomp doesn't get initiated. And hopefully it makes sense that if you can do this, right, jail avoided, there's going to be a previous level that looks exactly like this, but without the jail happening or this backdoor. And if you can kind of squeeze this into that solution, basically, I mean, you might have to be a little bit careful, right? At some point, we need to get some shell code. We need to deal with all of this, this stack smashing detector, but a previous level covers that. So if you're asking about 5, hopefully this is what you're interested in. If you have more questions about 5, please ask in chat real quick. Otherwise, we're going to look at another level. Go level 7. All right, people are done with level 5. I think that's enough to get started. Thanks. Okay, yep. Hopefully this kind of idea mixed with previous levels will work out. Oops, that is not what we want. Level 7. Workspace. Okay. Level 7, the very fun level. Okay, so back to the Yawn 85 world. We have ourselves a Yawn 85 emulator. You'll have to reason about Yawn code. So if anyone watching this has not solved hopefully multiple of the Yawn 85 levels, so I think it's the second to last reversing level that has you actually write Yawn 85 code. At a minimum, hopefully you've done at least the first one, or hopefully you have some understanding going into this of what Yawn 85 looks like and how it operates. If you haven't done that already, I would highly encourage you to go back and solve that, because this is just going to immediately expand upon that. So whereas in the reversing, you just have to reverse and understand Yawn 85, here we're kind of expecting you are going to have understood Yawn 85, and maybe you'll have to understand some modifications or whatever, but you should hopefully, I would strongly encourage you to go back and solve some Yawn 85 levels if you are here and have not solved Yawn 85 levels, because otherwise it'll be very difficult. Okay, so it's telling us, I guess there's a bit of a bug here, we're missing that, but whatever. This time you're in control, please input your Yawn code. And then it gives us some more information saying, and this is kind of different than a reversing level, this challenge doesn't allow you to call open via the sys instruction, but luckily it makes a memory error, so it's just straight up telling us there's a memory error, that will let you accomplish your goals. Okay, so it's telling us that there is some sort of memory error going on here. So I think the thing that should start as you kind of start solving these memory corruption levels and these toddler levels that involve these memory corruption levels, and now we're in kind of a more complex program than previous levels, right? We have like actual program here rather than just kind of this bare bones thing meant to be exploited. We have this real actual potentially useful program. It's maybe not that useful, but it's a real program. We now have to consider an aspect that hasn't really been covered until I would say this level, which is using reverse engineering and this understanding of memory corruption together to kind of search for bugs. Like you have to actually really hone in and find the bug in the program. So it's telling us there's a memory error, so that's nice, right? If you think you go and look at an arbitrary real world program, and there's probably a memory error in it if it's sufficiently large, but this is telling us, which is kind of one of the nice things about CTF, we know that there's a problem here. But either way, we still have to find that problem. So the first thing that I think should probably start coming to your mind when you're looking for a way to exploit this more complex program is, what are the ways that we can influence this program? What are the ways that we can send input to this program? Because our input is ultimately what is going to control the program and allow us to start controlling corruption and start really taking over the program, right? Without our input, there's no real sense of what's going on. So I would look into everywhere first. The first thing I would look into, and there's follow-on steps, but the first thing I would look into is all of the ways that this program is going to take input. So immediately it's telling us, this time you're in control, please input your Yawn code. So hopefully the very first thing that you think about is, just at a very basic level, what if I send 1,000 A's to this thing right here? Please input your Yawn code. is there potentially a buffer overflow here? If I send it 1,000 A's, am I gonna like seg fault? So if we launch x.py or create an x.py so we can start quickly testing these sorts of things, we will send after good luck. We're going to send, let's say, 1,000 A's. A times 1,000, just as a very quick check. So we could use reverse engineering as well to like look into what's going on with this, read syscall, and understand it better. But for now, we're just going to test it. Like, let's just immediately jump in and test and see what happens. So we don't care about that. Let's run this. Python x.py. So we just sent 1,000 A's. So we did have some sort of crash. It says machine crash due to unknown register. But we didn't get a seg fault. If it was able to tell us this, that means it probably didn't seg fault. If we do target poll true, like pwn.info, we can see what the exit code is, see if like it's -11, for instance. If we do that, how do I get this? What do I want to do? Target.interactive. Trying to think about how to get this next line. Oh, I think we just needed to make this a stir. Okay. And we see that it outputs once, like not -11. It's not seg faulting. Hopefully that's clear. That a machine crash is kind of this Yawn 85 construct, not a this ELF, this program running on the processor's dereferenced memory that isn't mapped and seg faulted. This is a logical crash in some sense, right? The program handled this. Okay, so I guess the question would be, is this enough? Like, do we know then that this read call that's happening here, is this safe? And to really start to understand that, we'd probably have to start actually looking at the program. So I am going to, I think I already have this open in IDA. Yeah, we do. Okay. Just to make sure, can someone say something if this isn't showing up the IDA screen? I think it is. I think I'm just sharing my desktop, so it should show up. But someone shout in chat if it is or isn't. Okay, but anyways, I'm going to keep looking. So IDA shows. Perfect. Okay. So we can see that this is main, and I've just set it immediately to decompile, just so that we can get a quick understanding. So this is that read I was talking about. So as we're in our journey of looking for a memory corruption, probably some sort of basic-ish buffer overflow, we're looking at the entry points. How can we send input into this program? So this is the read we're currently investigating. So it's going to this buffer which is size 1024, and we're reading in hex 300 bytes. So maybe we change that to decimal just so these match up. So we can see we're reading 768 bytes. At least according to the decompilation, it thinks it's 1024. If we look at this right here, can I change that? No. Let's make, I can't change that either. Either way, moral of the story is this buffer is larger, or maybe the same size, as this, or how do I want to say this? So RBP minus hex 410, right? So we're hex 410 away from the saved base pointer. We're reading in 768, which we just saw before is hex 300, right? So we're reading 300. We're still going to be hex 110 bytes away from the saved base pointer. So it's very clear from that, looking at this program, if this is all we're reading in, there is no chance that this read is going to overwrite the saved base pointer, saved instruction pointer, or something that's going to allow us to hijack control of this program. So this is, I would immediately kind of cross this out of my mind in terms of an immediate buffer overflow anyways. So something you might consider, right, is that we're reading into this buffer. Later on, we might start copying from this buffer, so still user-controlled input. We might start copying data out of this, and there might be a memory corruption as a result of moving memory around, which I don't know if we've seen levels like that before, but it isn't just when we're immediately like kind of this 0th order when we're receiving the data, that's where the corruption has to happen. It could happen after the fact of moving the memory around, but it all needs to kind of fall back to our user input in some path. But this 0th order is not going to have memory corruption, or that's not even exactly true. It's not going to have memory corruption that's going to overwrite the saved instruction pointer. It might overwrite some sort of metadata or other data. So for instance, maybe this was really supposed to be hex 200, and this following hex 100 bytes is going to be used later in the program, and we're kind of overwriting things that shouldn't have been overwritten, and it's going to get a little bit more of a logically memory corruption issue, not just an immediate overwrite the saved instruction pointer. But moral of the story is this is not going to allow us to immediately overwrite the saved instruction pointer. And there's another issue, which is even if it did, can we get to this return? And there's an issue here with this interpreter loop, which is this goes, that's not true. Is there a way to get out? If result equals FF. Okay, maybe I'm lying. Well, not about what I said before. So in theory, maybe we could get to that ret still. I was thinking that this loop was literally forever, but it looks like there is a way to get out of this loop, which means get out of this function, which means get to this return. So in theory, if it had been sufficiently large, we could have gotten to this ret. So that's like another thing to think about, right? It's not just enough to overwrite the saved instruction pointer, but we have to actually get to the ret instruction, which might be very challenging. As we've seen in previous levels, right, where, for instance, at seccomps itself, if you don't kind of correctly overwrite this value, or it exits if you don't correctly overwrite this value, you have to actually get to the ret as well. You want to both overwrite saved instruction pointer and get to the ret. Okay, either way, though, we can't overwrite the saved instruction pointer. Are we done? Is this the only place that we read in data? So we could start investigating this further and basically see every operation that follows from this memory that goes into this buff and see how it interacts with the rest of the program, kind of going, if you imagine like we have our input come into the program and it kind of branches and flows throughout the program from there. We could start exploring those branches. Or we could ignore that for a second, not kind of depth first search through this exploration process. We could do breadth first search. We could see where else can we receive input into this program. So if we do a, how do I do this? If I do double click this, this is the read function. So we could actually look over on the left, and it's probably a little bit small, and see all of the libc functions being used to see kind of what could take in input. So we know that read will allow the user potentially, I mean, maybe it's reading from a file and not actually a user controlled file or something, but this is an input method, read. There's no other input method. So like there's not like a gets, for instance, or like a scanf or some other function that theoretically could be used for receiving user input. There is an execve, which could be interesting if we could somehow control data going into that execve. As it turns out you can't, but maybe that's another kind of side tangent to think about. But where else maybe does it call read? So if we click, or if we hit on our keyboard X to do xrefs, we can see that main was calling read, which we just saw, and we kind of validated as immediately okay-ish, at least in the 0th order issue. But there's these two other reads. So we have this read and this read. So these are potentially places that user input could come through. And hopefully, if you've already done a Yawn 85 challenge, you will know that this interpret sys is kind of the Yawn 85 machine equivalent of the syscall instruction. So these are the syscalls that we can make. And we can see that from the help text that was talking about disallowed system call sysopen, this is kind of where it implements that. So if we try to do an open syscall, here's where the machine will just crash itself, kind of as a pseudo seccomp-y sort of thing. If we look at this. So if we think back to previous Yawn 85 levels, we know that there are two variants of the kind of read syscall. We have one for reading in code and one for reading in data. So this kind of implies, and we know from reversing in previous levels, that there's kind of this code region of memory and also this data region of memory, and these are syscalls that control the ability to read into those. So read in more instructions, read in more data. So these are two potential points, right? If we just start reading in data, then in theory we could have this 0th order buffer overflow issue. And hopefully it makes kind of sense with like what I've been saying with like the 0th order versus higher order memory corruption issues, kind of like something immediately stemming from this read and just going straight to the saved instruction pointer versus something sitting in memory and being manipulated later on to cause memory issues. Okay, anyways, looking at this. If we look at this logic, and we know from previous reversing levels, I'm not going to set up the struct. We're just going to kind of go off of previous Yawn 85 knowledge. We know that we have our register values stored in this VM object. So this A1 being passed is kind of our VM object. And this VM object, this Yawn 85 VM object that keeps track of our code, keeps track of our memory, keeps track of our registers. This A1 1026 looks like it's probably like the register-ish area. So A1 1024, we can see, is going to be, when we do our read syscall, this is going to be what file descriptor we're reading from. This is going to influence where we're reading to, and this is going to influence how many bytes we're going to read. So if we look at this, and these are all things, unless the program's changed significantly from previous Yawn 85 levels, these are all things that we can control by creating Yawn 85 code to kind of like set these values, right? So if this is, if it's following kind of from previous levels where the very first thing that we're using is our A register, if we did like an immediate A0, we would set the A register to 0, and now we'd be reading from standard in. Where would we be reading to? We would be reading to, I guess, 3 times A1 1025. So that kind of implies that if we could make this be 0, this 1025 thing, we'd be reading straight into the beginning of the VM object. And maybe that's okay. Maybe the very beginning is where our code is stored, probably is, kind of based off of this logic. And we can see kind of later on this read memory, it's doing A1 1025 plus 768. So probably 768 is the offset for data. It's doing this 3 times, which maybe makes sense because we've got 3 bytes per instruction. So maybe what we're passing here as a value is the number of instructions we want to read, which we have to multiply by 3 to get the number of bytes to read in. And this is how many bytes. So, okay. So this A1 3 times 1025. Okay, so we control this. So we specify where we want to read in data. But these values are bounded, at least according to previous levels. Maybe it's changed, so we'd have to investigate more. These values have to be 0 to 255. Actually, we could probably see that through the decompilation. Yeah, that this is working with 8-byte 1-byte values, 8-bit values. So we're kind of bounded by, assuming the decompilation is doing all of its type information correctly, this value can only be 0 to 255, which means at most we could get to this 768 actually. So we can get, when we read in code, we can get right up before memory, if we think about this layout wise. So that means we can't like read in code that's then going to overwrite memory or something, it seems. And V3, I guess, is calculated. So we're not just passing a register here. we're doing v3 equals one of our register things. And then we're doing if 3 times, so the kind of number, this is like a conversion from instruction size. I mean, this is instruction size, right? 3 is our instruction size. So where we're reading to, right? If we look at this, A11025 is kind of where we're reading to. And this is 3 times, so this 3 times kind of factors in. So this is where we're reading to. It's basically saying, and then this is going to be our 768. We're just kind of factoring in these 3 times. So 768 minus 3 times this. If that's less than v3, if this is less than v3. So we can imagine the case where this is 0. So we would have 768 is less than it's less than this value. So I'm just kind of in my mind testing edge cases of this. So if this was 0, so we know that all of these A1 bracket things we can set anywhere from 0 to 255. So what happens if we put 0? What happens if we put 255? If we put 0 here, we have if 768 is less than this. 68 is less than this register, so it's not. Which means we just straight pass in. This is where we're reading to. V3. Just trying to think of the memory implications of this stuff, which is kind of the crux of this problem, right? 3 times 256 minus this. Okay, here's one way to think about this. So basically, if this whole value, right, this whole value which gets repeated in this inside this condition, if this entire value is less than v3, so if it's less than v3, we just set it to be that value. Okay. So if this thing is less than v3, so we're kind of bounding this value by this. So 768. Yeah, and someone's pointing out in Twitch chat, right? So this is, I'm having a hard time understanding and therefore explaining exactly what this is. You'd have to probably use like pen and paper, really reason about this expression. But it's doing some sort of check on how many bytes we're going to read in. Because we can imagine the case where we make our register be 256 and 256, right? So we want to, if we imagine this at a higher abstraction level, right, at the Yawn 85 level, how is this program going to handle the case where I want to read to memory at the very last location of memory, and I want to read the maximum amount of bytes that you'll let me. So 256. So if we go all the way to 256, all the way to the end of this memory section, and I say I want to read 256 bytes, what is the program doing to handle that? Like, is it going to do this modulus thing where it like loops memory around? Is it going to just cut it off? What's happening? And what this logic is doing is it's cutting it off. It's basically saying, if this was 256, so imagine the case where both are 256, or I guess 255. If both are 255, then this is 1. This reduces to 1. And it's basically saying if 3 is less than 255, right? So this would become if 3 is less than 255, we're imagining both being 255, 255, 255. If 1 is less than 255, which in this case it is, then we are going to do this. This is going to be reduced to 1, 256 minus our 255, so 1. It's basically going to say, all right, I'll let you read 3 bytes, right? This is how many bytes are going to be read. In this case, if you do 255, 255, I'm going to let you read a byte. Okay, which could be an off by 1. I'd have to think about that, depending on where exactly. So if it is 255, so even like a 1 byte memory corruption could be a big deal. If it is 255, and we're still going to let it read in 3 bytes. We're going to be reading to, it seems to be, it's not going to be overwriting into here if this is at 768. So maybe this is still part of its memory. There's kind of like this 3 byte region. It's going to be reading into plus 765 through 768. So maybe there's an off by 1 there. Maybe we were able to read in 1 more instruction than we should be. I'm not entirely sure. We'd have to kind of look deeply into this. But yeah, either way, the important thing to look at is this next one, which doesn't have this like if check thing, which is very suspicious. We know that it's doing bounding checks on this. Now it's possible that it's like optimized in a way where it doesn't even need to do checks, because even if you pass 255, 255, it's not going to be an issue. But we'd have to investigate that. I'm looking at chat real quick. If you compare it with the old baby rev levels, you can see the check should be there, but isn't. Yeah, so in previous baby mem levels, this sort of check did exist here. And suddenly that check is gone. So that is highly suspicious, right? If we think about it just from a meta challenge perspective, right? Why would this safety condition just vanish? And we tell you, hey, there's memory corruption. Very, very suspicious. So now what we would probably want to do is try to test this and see what happens. Can we put in the largest values we can, our 255 and 255, right? We want to read 255 bytes and we want to go to the very end of this memory section. What happens? That's going to be probably the quickest way to really understand it. We could follow through A1 and the memory implications and everything, or we could just write some Python and see if something crashes. That's kind of like let's just test this, see what happens. Now we're not guaranteed, even if this is a memory corruption, that it's going to be a crashing memory corruption, but let's just test it. Okay, so in order to test this, we need to exercise this. We basically need to write some Yawn 85 code that's going to get here. Okay, so we want, okay, I think since we're in the teaching modes, we can kind of speed up our reverse engineering a bit by looking at the print statements. Decompiling. Why are you taking your sweet time decompiling? Okay. Let's hit F5. Okay, it figured itself out. Okay, so this is going to tell us the numbers for our registers. So we have, and we remember 1024 was A, B, C. So these are the things we need to control. So if we just quickly write Yawn 85, or what do we want to call it? Like A register equals 1, B register equals 4, and C register equals 8. Hopefully by now maybe you have some code that's, I don't know, some structure for being able to quickly write Yawn 85 code. But we will build something ourselves here real quick. So we have 1024, 1025, 1026. if we go back to interpret sys, so 1024, 1025, 1026, those seem to be the things we care about. 1024, 1025, 1026. Okay, so we want to, if we think about, I guess there's a question or a statement, why my code never shows switch cases beautiful like that before I fix them. I don't know. Maybe I haven't reversed this enough. Maybe there's a reason that it doesn't know how to switch case it. I'm going to guess that it's at least giving you some decent-ish if-elses, but yeah, I'll agree the switches are very easy to read. Okay, so we know this is what we want. So we want to do, we want to test this. So the other thing we need to know is what is our immediate instruction. So interpret immediate so that we can set those to values that we care about. Here. So it looks like this needs to be hex 10. Interpret immediate equals hex 10. And we care about interpret sys. Sys is this. Why does this look slightly different? Does it? I don't know. Either way, and 4. So interpret sys equals hex 4. So this is all we need to know in terms of constants. Well, actually, we also need to know our instruction ordering. So we can look at this actually. This will tell us, because we're in the debug mode, it tells us our order. So it tells us that the op is just taking A2 and casting it to an int. So that's the 0th. Argument 1 is byte 2, which is the 3rd byte, because it's 0 base. This is kind of like byte 0, byte 2, byte 1. So we can say that op equals 0, arg1 equals 2, arg2 equals 1. So that's kind of our ordering. So now if we want to test this, what we want to do is trying to think about this. If I want to write something advanced or if we just want to write it out by hand. I think we're just going to write it by hand. It's going to be just fine. Do we want to do that? Yeah, why not? Yawn 85 code equals. I guess we can use it by these names. So we want to do an interpret immediate. Oops, interpret immediate. And we want to set our arg1, so that's going to be the second value. So what value do we want to set it to? 0, and we want to do a register. So basically what I'm saying here is interpret immediate, set A to 0. So that's going to allow us to read from standard in, basically. So if we think about the very last thing we're going to do is interpret sys. I don't actually remember. Interpret sys. What are the args to this? Don't know if it matters for our purposes. A1. So we're writing to A2. Byte 1. Does byte 2 not get used? I think only the. I think only op1 or arg1 gets used. And I think it's the register that we're writing the result to. Yeah, that's what this looks like. So we're just going to put a 0 there, and let's just make it so when we do our sys call, it's going to just write the result to A. Okay, so this is going to be, we'll say, A equals 0. FD equals 0, basically. And then we want to do, we said we want to set B register to 255, our maximum value. So B equals 255. So we'll just say like buffer equals 255. That's not exactly true, right? It's on the stack, but it's kind of how far in we're gonna be ish. Interpret immediate 255 C register. How many bytes we want to read? So C equals 255. Count equals 255. So this is about to do our Yawn 85 syscall. So we'll say Yawn 85 ASM equals join. How do I want to do this? Actually, can I just do bytes? I think we can just do bytes of this. Bytes of Yawn 85 code. Okay. And just to be sure, we'll do pwn.info Yawn 85 ASM. So now what we're going to do is we're going to send our Yawn 85 ASM. We're going to go interactive. And we'll leave that for now. We don't really care though. We're going to probably have to write some more data after this, but let's just see what happens. Okay, something went wrong. What went wrong? Sleep. Oh, one of these things is that's what the other register is. At some point we need to specify which syscall we want to do. Is that going in op2? Wait, I think I'm thinking about this wrong. Byte 2. Okay, yeah, we have this backwards. So we have to remember that this is op2, right? Op2. And op2 is byte 2, is byte 1. I'm probably saying this a little bit wrong. It's important to look at this rather than just listen to me ramble about making sense of this byte orders verbally. V2. Okay, either way, byte 2 is the syscall number. Okay, so the syscall number, and we want to do read memory. Well, this is a mess. I think it's going to be hex 10. I think 0000 is just like being ANDed with the register value or like the other parts of the instruction. I think, yeah, because we can see like if we highlight the 0000, so 4 of the zeros, we can see this is 2, this is 8, this is 10. I think, remember right from previous reverse engineering of Yawn 85 that this should mean it's 10. So we should say sys read memory equals hex 10. And we're in we're in the teaching mode, so we'll know for sure. I think so we need to move. This is our destination, which needs to be there. Sys read memory needs to be there. Does Python let me have a comment there? Or a comma? We'll see. Oh boy, what did I just do? Okay. Python x.py. Okay, we did what we wanted. We're reading from memory. And if we strace this, what's the easiest way to strace this? If we do this, we're running. Oh, we're not in practice mode. If we do set UID, is this going to work? Set UID equals false. I just want to confirm that we're doing the values we want. If we do this, Control Z, PS, PS-A. Did our process get killed? What's happening? There it is. This. Can I strace attach? Strace that. P. Strace P that. Oh, is it not going to tell me? Well, that's so sad. I'd have to finish the read call. I basically just want to confirm that it's doing a read with 256 or 255 bytes being allowed. Start another terminal. All right, we'll do that. This. strace. That. Okay, so we're attached now. We go back to. How do I get to the other guy? Oh, it's over here on the left. This. I do foreground now. Okay, we're doing our read. If I type in test, crazy stuff happens, but oh, well, I guess all of this happens as well over here. Okay, what I wanted to just quickly confirm, apparently it's not worth the effort because it took longer than just assuming we were right is, but we wanted to just check, make sure we're reading 255 bytes. We didn't like somehow mess up our Yawn 85 code. Sometimes it's nice to go a little bit incremental, make sure that what you're doing is actually what's happening. Turns out it is. Okay, anyways, enough of that. Let's kill that terminal. So we know that it's going to read. So what we want to do is we want to target.clean. And let's just do timeout equals 1. So what this is going to do is it's just going to, I mean, maybe it's easier if I say read repeat. They're the same thing, I think, or very similar if not. We want to read just for a second, just continuously read for a second. Basically, we're just stalling out for a second. And then just to make sure that we don't concatenate our two things together, because then we're going to do write a times 255. So this, we're just guaranteeing that somehow these 255 A's don't get joined up with our assembly, and we'd have a very bad time if that happens. So let's just add a 1 second sleep here, basically. We could also literally just do a sleep. Okay. And let's see what happens now in our testing of our memory corruption. Be very cool if we get like a seg fault. That would immediately confirm, yeah, we definitely have memory corruption. Of course, we could still have memory corruption even if it doesn't seg fault. We might be overwriting other data that's useful that can have higher order memory corruption primitives off of, but it'd be super cool if we just immediately crash the program to confirm this. And -11. Maybe it'll be cooler if we do a read all here. I think target poll true. If we do this now, watch this. Wait, why isn't that telling me? I thought it like says like process exited with sig fault. Okay, either way, very cool. We've got our -11 we wanted. Does that confuse anyone? Does anyone have questions about that? That we just crashed the program, and this is very, very cool to crash the program. Are there any questions on why crashing the program is cool? I guess we can immediately show why it's cool in a second. Target read all. So we got our -11 as we were talking about, and we have setuid equal to false. So if we do ls, make sure that this core was just recently generated, date, was it? Let's just be safe. There's no core file. We run it again. And the reason we have the ability to potentially get a core here is because we did this setuid equals false, which otherwise would be running suid, and that suid is not just going to core dump and let you read memory. Oh, and I guess we can also see what I was going to show because we're in debug mode. The saved return address is now pointing to A, as in these A's that we just sent it, almost certainly, maybe there could be some crazy coincidence, but almost certainly we have control over where we're returning to. Very cool. Okay, and do we have our core dump? We do. Wait, why? Oh, I'm mixing. I was thinking that this is like 250 set. Yeah, okay. These are the same time. Okay. And just if we didn't have teaching, right, we're in testing mode, or you're in some other program that doesn't tell you where saved instruction pointer is about to go, or where we're about to return control flow to, we get our core dump, we run the challenge, we pass the core dump path, we look at this, we see X8I, RIP, I guess this isn't immediately telling us, but if we now do, we're about to do a ret, which is where we crashed, and if we do p/x or xgx rsp, we can see that when it crashed, the reason it crashed is it couldn't go through with this ret instruction of setting the instruction pointer to be the first thing on the stack, these A's. Okay. Does the process still exist at that point? Oh, you're asking a different sort of question. Okay, so when sig fault gets printed, what is writing to standard out at that point? Does the process still exist at that point? I believe, so there's kind of two options in my mind of theories of who's doing the writing of sig fault. So well, I guess there's a few options. One option would be that libc registers a seg fault handler, and it's actually able to catch its seg fault, catch itself seg faulting the program, because libc would theoretically be doing this. And then that could be the thing that writes to standard out or standard error or whatever. But that's not who does it. And we would see that probably in the core dump that would mess with things, because unless it then restored back, it would have to do some weird things if libc was responsible. I believe it's the parent that does it. As in, let me think here. Yeah, I think bash, for instance, has that string. I think the parent, when it does, so when it, if you think about your shell, right, it's going to, when it wants to start up a new process, it's going to fork and then exec ve, and then the parent, which wasn't the PID equals 0, is doing a wait on that child. And when it gets the wait, it's getting the exit code back. And I believe it's checking that exit code and then printing segmentation fault occurred. I believe it's bash. I don't think it's the terminal, right? The terminal is just a file. I believe it's bash, so your shell. Smash stacking detected is different. That is libc that's printing that. So if we do, and this is kind of a side tangent sort of thing, but I love these sorts of questions. This is how you really understand things, is you say, hey, how does this work? And you go and investigate. If we look at this, if we just do strings on, oh, that's not what I wanted to run strings on. If we run strings on libc and we grep for, hopefully you said it right, smash stacking, stack smashing detected. Yeah, we can see that this string exists within libc, which is a very strong indicator, right? That's the guy that's doing it, and it is. And it makes sense because you're calling stack check failed or whatever. And that's going to call into this, it's going to output, and it's just going to end. And I believe, yeah, that this is writing to standard error when libc does this. So that's a libc construct. But the segmentation fault, is that, how does that, I'm trying to remember what the error is. Segmentation. Does it just say segmentation fault, or? So that string exists. But that doesn't mean that it's the libc. This doesn't mean that it's our program that's printing out segmentation fault necessarily. And I mean, I guess this one doesn't either, but we know, I can tell you for sure that this is your program is actually printing out this because it's able to call into a libc function to check it and it's able to error itself out. But this is like a CPU issue, right? Like the CPU reaches a fault and the process just gets killed as a result. I believe the interrupt will happen, the kernel will take care of it, and it's basically going to say, yeah, this process just seg faulted. It'll let any, it'll redirect that fault off to any fault handlers or any, what's the word? Like a fault, yeah, some sort of fault handler. If one is registered, but I don't believe one would be registered by default, but I do believe that bash has it. And what you could do is you could strace bash and crash yourself. I don't know. I've gone down this rabbit hole before. I'm 99% sure it's bash that's doing this when it does its wait logic. You could also look through the bash source code and see where it does its fork wait stuff. Okay, anyways, enough of that fun. So are there any more questions than on level 7? Hopefully this is more than enough to kind of get you started and kind of really understand how you approach finding a memory corruption error. So this is still a bit basic-ish, right? You could imagine that these memory corruption errors could get really complicated really fast. So in this case, we have still just a straight read syscall. It's not the very first read syscall that happens, not the very first point you can input data into the program. It's a later one, but still it's just a straight read into overwriting a saved instruction pointer. It can get a lot more complicated. Okay, and someone in chat says, I got 7, sweet. Okay. So then there's another person in chat that asks, how would you approach the JIT spring level, which I believe is the very last level here. And this level, so as I've been saying, kind of you could imagine much more complex ways that a memory corruption could manifest, that you can't just immediately send a bunch of A's and see the program crash and like, boom, confirmed, we got memory corruption. There's cases where you send some data and then it doesn't crash. And then you interact with the program in a bunch of weird ways and then suddenly it crashes, for instance. Or maybe it still even doesn't crash, but you overwrite some data and now suddenly the logic doesn't make sense of what's going on in the program, and it can get really complicated really fast. It doesn't have to just be immediately read syscall, overwrites instruction pointer, crash, boom, done. It can get very complex. Yeah, so that part of that side tangent with libc having grep segmentation. If you read through the source code of libc, you're going to see that the string associated with this is there's some sort of function that's able to ingest a signal number, like a -11 or 11 or whatever, and basically turn it into a string. And that is why that string exists in libc. I believe bash is calling into that libc function after it does await on its child, and then using that libc basically convert a number into a string to report segmentation fault. Okay, so anyways, back to like if we have JIT spring levels. So this is definitely a level where it gets a lot more complicated. You're not able to just read in data and insta crash yourself, I believe. Is that true? I'm trying to remember the bug or how the bug actually manifests. Maybe you could. I don't know, but either way, I don't think so. So either way, the question is, how would you approach the JIT spring levels? Let me think of advice. So we were looking in IDA basically at all of the points. Okay, so there's a number of ways to think about this, of how you even begin to tackle the idea of a memory corruption and detecting that with like a crash and then converting that into like remote code execution by hijacking the saved instruction pointer. This is kind of like the basic route that we've been showing, but there's multiple ways to hijack control flow execution. You don't just have to overwrite the saved instruction pointer. You could also overwrite, for instance, a function pointer. And if someone, you could imagine if you have some metadata that lives in some structure and you have a function pointer in there, and you're able to do memory corruption that overwrites that function pointer and then trigger behavior that's going to actually call that function pointer later on. Well, now you've also hijacked control flow. It doesn't just have to be, so the simplest hijack, right, is overwriting the saved instruction pointer. And I guess I wouldn't call that necessarily a function pointer, but it's a code region pointer where control flow is going to suddenly diverge back to or to. And so for instance, I guess if we think about function pointer, right? Hopefully, is everyone familiar with the idea of a function pointer? So if we just think about this real quick in Python, which is going to be way more complex, maybe we should do it in C. But if we just think like, hey, we have this function test, and we do print test, this is all this function does. And we have this other function like hello, and it takes an argument. And let's say it takes an argument which is a function. And then this function is going to do hello, and then call that passed in function, and then print an exclamation point, for instance. Now what we can do is we can pass a function to this, right? This argument isn't like a string or a number. This argument is a function. And it's a function that can then be called, right? We didn't call test here. We called an argument being passed in. And this is basically the idea of a function pointer, is that you want dynamically a function to be called. And the same, you can do this exact same sort of thing in C. The syntax is a little bit weird, basically because you have to specify a type, and the type, you have to specify it as like a function pointer. I'd have to Google it for the exact syntax. It's like, if it's a something that returns an int, C function pointer. Just Google it. It's easier. I don't remember the exact syntax, but we can see here this. Like this is the, so this is the name. The name is fun pointer. And then this is like how you get that type info in, because, you know, see, you need the type info. So this is, we have some function fun, and we want to pass it somewhere. Or in this case, they're just immediately creating a local variable and then calling it what just happened. Okay. So this is the same idea, but yeah, hopefully that makes sense. So I think all of the levels you've seen so far, the way that you achieve code execution is by hijacking the saved instruction pointer. But it is also equally as valid, though slightly more complex potentially, to immediately notice that you can just overwrite a function pointer that just exists in some structure somewhere. And that will be a useful concept in later levels, because you won't be able to just overwrite the saved instruction pointer, right? There's going to be, for instance, a canary in the way. This canary is going to block you. or maybe it doesn't do a buffer overflow that reaches the saved instruction pointer. It does a buffer overflow that just happens to accidentally overwrite a couple of bytes of some other thing. Maybe that other thing is a function pointer, or whatever. So that's kind of the idea of where these memory corruption issues can get a bit more complicated, both in terms of noticing and then also, yeah. Okay, and are there any more questions? I think I'm probably going to be wrapping up the office hours soon-ish. But I can take a couple more questions if there are any more. Good for today. Just keep grinding towards 11 right now. Yep, it's the fun part. Definitely can get tricky, but I guess that's how you learn. All right, well, I am going to end my office hours. There will, of course, be Q&A tomorrow, I believe, and you can always ask questions on the Discord. So thank you, everyone, for watching, and see you next time.